Hello and welcome to The Sleepy Scientist. This is your quiet corner of the internet where we let curiosity roam, but never in a hurry. Tonight, we're taking a gentle wander through one of the universe's most fascinating rules, the speed of light. But before we start, I'd like to know, where in the world are you watching from? Are you tucked up at home, listening from a cozy bed, or perhaps somewhere with a little nighttime background hum in the air? If you're enjoying these peaceful science explorations, I'd be so grateful if you could give the video a like and subscribe to the channel. And to those of you who are already subscribed, truly thank you. You're part of the reason this little community of stargazers, thinkers and midnight dreamers exists. Now I should warn you. I hope this video isn't so interesting that it keeps you awake, but if it does, at least you'll drift off knowing a little more about the universe than you did yesterday. So, let's settle in and take our first step into tonight's journey. After all, what could be so fast, so constant, and so unyielding that it defines the very limits of motion in the cosmos? When most people hear the phrase speed of light, they imagine a single fact, a number so big it's almost meaningless in everyday life. But the truth is, it's much more than a number. The speed of light is not just a statistic you memorize in school, it's a rule woven into the very fabric of the universe. Light speed is the reason we see distant galaxies as they were millions of years ago. It's why time itself bends and stretches for objects in motion. It's why the universe has a visible edge, and why nothing, no matter how ambitious or how determined, can outrun it. In other words, to understand the speed of light is to understand one of the deepest and most beautiful truths about reality itself. Over the course of this journey, we'll step softly through the history of humanity's attempts to measure this elusive constant, from ancient philosophers who thought light travelled instantaneously, to brilliant minds who built ingenious devices to catch it in the act. We'll explore Einstein's realization that this speed is more than a property of light. It's a fundamental feature of space-time itself. We'll peer into the strange worlds of quantum physics and cosmology, where light sets the ultimate speed limit but space can still play its own tricks. We'll talk about why light travels exactly as fast as it does, how it changes when passing through water or glass, and why it slows down without ever truly breaking its own rule. We'll meet the other cosmic travellers that share its speed, from gravitational waves rippling through space-time to hypothetical particles we've never quite caught. And we'll look far out into the cosmos, where the speed of light becomes not just a measurement, but a messenger from the past carrying the story of the universe straight to our eyes. Don't worry, there will be no equations to memorize, no impenetrable chalkboard scribbles, and no mental gymnastics. This is not about struggling to keep up with the physics, it's about taking a comfortable stroll through it, seeing how the pieces fit together, and pausing to admire the scenery along the way. And maybe, just maybe, by the end of this journey you'll see light differently. Not just as the thing that lets us see, but as the quiet, unwavering heartbeat of the cosmos. Because once you understand why light moves the way it does, you start to see the universe in motion everywhere you look. When we talk about speed in everyday life, it's usually something we can picture easily. A car zipping down a motorway at 100 kilometers per hour. A runner pushing for a personal best at 20 kilometers per hour. Even your morning coffee seems to have a speed, the way it slides across the counter when you nudge it, or perhaps more importantly, the rate at which it wakes you up. In these familiar moments, speed feels simple, it's just how fast something goes from point A to point B. But in physics, speed is a little more than the number on a speedometer. It's a fundamental quantity, a measure of how far something travels in a given amount of time, usually expressed in units like meters per second. That sounds straightforward enough until you start to consider how the choice of units, and even your point of view, can change the story entirely. For example, let's take a jogger on a beach. If you're standing still and watching them pass, you might measure their speed at a steady pace of 8 kilometers per hour. But if you were running alongside them at the exact same pace, their speed relative to you would be 0. From your point of view, you and the jogger aren't moving at all. This is the idea of a frame of reference, speed is always measured relative to something else. There's no such thing as absolute speed that works for every observer in the universe. This relativity is easy to imagine at human scales, but things get strange when you stretch it to cosmic distances and velocities. At low speeds, the differences between frames of reference are just simple arithmetic, your speed relative to the ground plus or minus the other object's speed. But once you get close to the speed of a light, the arithmetic changes into something far stranger. Distances shrink, time dilates, and the whole concept of when and where becomes slippery. Before we get that far though, it helps to be clear about the difference between speed and velocity. They're often used interchangeably in everyday speech, but in physics they are distinct. Speed is simply how fast something moves, without regard for direction. Velocity, on the other hand, includes both speed and direction. If you change direction but keep the same speed, your velocity changes, something that becomes very important when you're thinking about orbits, waves, and anything that curves rather than moves in a straight line. Speed can also be averaged over a journey, or measured at a specific instant. Your average speed might be 50 kilometers per hour on a road trip, but at any given moment you could be moving faster or slower depending on traffic. Physicists call the right now version the instantaneous speed. At the atomic level, particles rarely move at a constant speed. They jitter, collide, and ricochet. So scientists often work with averages taken over enormous numbers of interactions. When we look up at the stars, the numbers become so big that everyday comparisons start to break down. Imagine trying to race a beam of light with your morning coffee. Even if you sprinted to your kitchen counter at world record pace, that beam of light would have already gone around the entire planet more than 7 times before you even touched your mug. At such scales, speed becomes more than just a number. It shapes how we experience time and space itself. In the end, speed in physics is both a familiar friend and a slippery concept. At human scales, it's easy enough to measure and picture. At cosmic scales, it bends our sense of reality and ties into the deepest rules of the universe. And the more you explore it, the more you realize that how fast is just the beginning of the story. If you could step back in time to ancient Greece, you'd find philosophers debating what light actually is and how we see the world around us. One of the earliest ideas came from the mathematician Euclid, who believed that vision worked because our eyes sent out rays, a bit like tiny searchlights, and these rays touched objects, letting us perceive them. It sounds strange now, but in an age without cameras, lenses, or even a basic understanding of the eye's anatomy, it wasn't an unreasonable guess. After all, when you open your eyes, the world appears instantly. Why not assume that eyes are actively reaching out to meet it? Plato added his own twist to this idea. He imagined vision as the result of 2 streams meeting, one of light flowing out from our eyes and another flowing in from luminous sources like the sun. Only when these streams met, he thought, could sight occur. Aristotle, on the other hand, leaned toward a different explanation. He proposed that objects themselves released something called form into a medium like air, which then travelled to the eye. Although still far from correct, Aristotle's approach was an early step toward the understanding that vision depends on light coming into the eye, not leaving it. For centuries, these ideas were accepted and discussed without rigorous testing. The world of ancient science often relied more on reasoning than experiment, and without tools for precise measurement, progress was slow. It wasn't until the Islamic Golden Age, over 1,000 years later, that a major shift occurred, thanks to a man named Abu Ali al-Hasan ibn al-Haytham, known in the West as Al-Hasan. Al-Hasan was a pioneer of experimental science. Living in the 10th and 11th centuries, he wrote the monumental Book of Optics, which systematically examined light, vision, and reflection. He rejected the ancient emission theory of vision, arguing instead that light travels from objects into our eyes. More importantly, he proved it through carefully designed experiments. By studying how light passed through apertures and lenses, he showed that vision was a process of receiving light, not sending it. His work also described how light travels in straight lines, how it reflects from mirrors, and how refraction bends it when passing through transparent materials. What made Alhazen's work revolutionary was his insistence on testing ideas rather than just thinking about them. He created controlled setups, using dark rooms, small holes, and angled mirrors to observe light's behaviour directly. In a way, he laid the groundwork for the scientific method itself. His writings influenced scholars for centuries, both in the Islamic world and in Europe, where his ideas were translated into Latin and became core reading for medieval thinkers. By the Renaissance, curiosity about light had become intertwined with the era's growing passion for measurement and observation. Galileo Galilei, in the early 17th century, attempted one of the first recorded experiments to measure the speed of a light. His method was charmingly simple, if not entirely practical. He and an assistant each carried a lantern with a shutter. Standing a known distance apart, Galileo would uncover his lantern, and as soon as his assistant saw the light, he would uncover his own. Galileo would then measure the time it took for the second lantern's light to reach him. The idea was to capture the round-trip travel time of light. Unfortunately, human reaction times are sluggish compared to light speed, so Galileo's experiment couldn't reveal anything useful. The delay he measured was entirely down to people, not photons. Still, his willingness to try reflected a growing shift in science, an eagerness to replace speculation with hands-on testing. In the decades that followed, other scientists refined these methods. Ole Rømer, in the late 17th century, used the moons of Jupiter as cosmic clocks, noticing that their eclipses appeared slightly earlier or later depending on Earth's position in its orbit. From these tiny discrepancies, he deduced that light has a finite speed. His work was the first real evidence that light doesn't arrive instantaneously, a revelation that marked a huge step forward in human understanding. Looking back, it's striking how this journey unfolded over millennia, from ancient philosophers imagining light as something the eye sends out, to medieval scholars carefully bending it through glass, to Renaissance astronomers timing celestial events. Each stage was shaped by curiosity and whatever tools the era could offer. These thinkers often worked with limited knowledge and imperfect instruments, but their determination chipped away at one of nature's most enduring mysteries. Even though none of these early figures knew the precise speed of light, their questions, and their sometimes flawed answers, built the stepping stones for those who would come later. Science, after all, is rarely a sudden leap. More often, it's a slow climb, with each generation passing the torch, or perhaps the lantern to the next. And in the case of a light, it's fitting that the very thing being studied was also what illuminated the path forward. In the 17th century, the question of whether light travelled instantaneously or at a finite speed was still unsettled. Many great minds suspected it had a measurable velocity, but proving it was a different matter entirely. Timing something so fast seemed almost impossible, the equivalent of trying to catch the wind in a jar and weigh it. And yet, in 1676, a Danish astronomer named Ole Rømer found a way to do just that without ever leaving Earth. Rømer was studying the moons of Jupiter, specifically Io, which orbits the giant planet with remarkable regularity. These eclipses and reappearances of Io from behind Jupiter's shadow were like ticks on a cosmic clock, and Rømer was carefully recording their timings. Over months of observations, he noticed something peculiar. The predicted eclipses of Io didn't always happen on schedule. Sometimes they were slightly late, sometimes slightly early, depending on the time of year. After careful thought, Rømer realized what was happening. When Earth was moving away from Jupiter in its orbit, the light from Io had to travel a longer distance to reach us, so it arrived later than expected. When Earth was moving toward Jupiter, the distance was shorter and the light arrived earlier. The variations matched what you would expect if light took time to travel. By comparing the timing differences, Rømer calculated that light took about 22 minutes to cross the diameter of Earth's orbit. From this, he estimated its speed to be roughly 220,000 kilometers per second, lower than the modern value but astonishingly close given the tools of his time. For the first time in human history, light had been caught in the act of taking its time. The result didn't just settle an ancient debate, it also opened the door for others to measure the speed with increasing precision. 2 centuries later, in 1849, a French physicist named Hippolyte Fizeau took up the challenge. Instead of using distant moons, he devised an ingenious laboratory experiment. Fizeau shone a beam of light toward a mirror several kilometers away. Between the light source and the mirror, he placed a rapidly spinning cogwheel. The teeth and gaps of the wheel acted like a shutter. When the wheel spun slowly, the light passed through a gap, bounced off the distant mirror, and returned through the same gap to be seen by the observer. But as the wheel's speed increased, the returning light would sometimes hit a tooth instead of the gap, blocking it from view. By finding the exact speed of the wheel where the returning light was just blocked, Fizeau could calculate how long it took for the light to make the round trip. From the distance to the mirror and the wheel's rotation rate, he deduced a value of about 313,000 kilometers per second, remarkably close to today's accepted figure. His method was not only clever but also entirely Earth-based, requiring no planetary alignments or cosmic clocks. The baton then passed to Albert Michelson, an American physicist with an extraordinary talent for precision measurement. In the 1870s, Michelson refined Fizeau's approach, replacing the cogwheel with a rotating octagonal mirror. Light was directed onto one face of the spinning mirror, travelled to a distant fixed mirror, and bounced back. By adjusting the rotation speed so that the returning light struck the next face of the rotating mirror at just the right moment, Michelson could measure the time taken with incredible accuracy. Michelson performed his measurements over increasingly long distances, sometimes stretching to tens of kilometers. Each refinement brought the value closer to what we now accept, 299,792 kilometers per second. His work eventually earned him the Nobel Prize in Physics in 1907, the first awarded to an American scientist. What's striking about these efforts is how varied the methods were, yet all served the same goal: to make the invisible measurable. Römer used the motions of worlds far away. Fizeau harnessed clever mechanical timing, and Michelson pushed engineering to its limits. Each was an act of patience and ingenuity, proving that even something as fleeting as a beam of light can be slowed, at least on paper, by a determined mind. By the end of the 19th century, the speed of light was no longer an elusive mystery. It had been pinned down with such confidence that it became one of the most important constants in physics, a benchmark against which other measurements could be made. What began as an astronomical curiosity had become a cornerstone of science, measured not just in numbers, but in centuries of human persistence. There is a number in physics so famous that it hardly needs an introduction: 299,792,458 meters per second. That is the speed of light in a vacuum, not an approximation, not a best guess, but an exact value written into the very definitions that underpin science. It is a rare thing in physics to have such certainty, and even rarer to see a measurement elevated into a definition itself. The exactness of this number is not because we can measure it with absolute perfection in a laboratory every time we try. Instead, we have flipped the logic. For over a century, scientists refined their measurements of light speed using increasingly ingenious methods. By the late 20th century, the value had been pinned down with such extraordinary precision that the error margins were vanishingly small. At that point, metrologists, the specialists in the science of measurement, decided that the speed of light was not just something to measure, but something to define. In 1983, the International Committee for Weights and Measures made a bold move. They fixed the speed of light at exactly 299,792,458 meters per second and redefined the meter in terms of it. The meter, once based on a metal bar kept in Paris, or on a fraction of Earth's circumference, was now defined as the distance light travels in a second vacuum in 299,792,458 792,458 of a second. In other words, light became the ruler against which all distances are measured. This approach has a beautiful symmetry to it. Time, thanks to atomic clocks, can be measured with extraordinary accuracy. Once you have an exact measure of time and an exact value for the speed of light, you automatically have an exact measure of distance. It is a neat marriage of two constants, one governing how we measure duration, the other governing how far something can move in that duration. There's also something quietly poetic about using the fastest thing in the universe as our standard yardstick. For millennia, humans measured distance in steps, rods, chains, or the length of a king's arm. Now every ruler, measuring tape, and laser rangefinder ultimately traces back to the steady, unwavering pace of light. The beams from a laser pointer at a lecture or a surveying instrument on a construction site are connected through this definition to a constant that is the same for every observer in the cosmos. It's a reminder that measurement is as much about choice as it is about discovery. We chose to make light speed a cornerstone of our system, not only because it is reliable, but because it is universal. Whether you're on Earth, orbiting a distant exoplanet, or drifting in interstellar space, a second is still a second, and in that second, light will always travel the same distance through a vacuum. There is a quiet confidence in building our measurements on such a foundation. It is as if we have taken something fleeting, a beam of light crossing empty space, and anchored it in permanence. The magic number may look dry when written out in digits, but hidden inside it is a story of centuries of ingenuity, a triumph of precision, and a subtle poetry that connects the smallest acts of measurement to the grandest scales of the cosmos. In our everyday experience, there is nothing to suggest the universe has a hard speed limit. Cars can go faster with more fuel, planes can break the sound barrier with enough thrust, and even a thrown ball can travel quicker if you have a particularly good arm. It's tempting to assume that if you just keep adding energy, you can keep accelerating forever. But the fabric of reality disagrees. The speed of light in a vacuum is not only the fastest speed we know, it is the ultimate speed, the one no object with mass can ever reach. This rule emerges from the structure of space-time itself, as described by Einstein's theory of special relativity. In this view, space and time are not separate, independent things. They are woven together into a four-dimensional continuum, and the geometry of that continuum dictates how motion works. Within this framework, the speed of light is more than a property of photons. It is a built-in feature of space-time, a kind of cosmic conversion rate between space and time. Imagine space-time as a vast landscape. You can move through space or you can move through time, but the combined speed at which you move through both is always the same. When you're sitting still, you're moving through time at the maximum possible rate, 1 second per second. As you move faster through space, you have to spend some of that motion budget on space, which means you move through time more slowly. This is time dilation. The faster you travel through space, the slower time passes for you compared to someone at rest. At everyday speeds, this effect is so tiny that you will never notice it without specialized equipment. But as you get closer to the speed of light, time dilation becomes dramatic. A spaceship moving at 99% of the speed of light would experience time passing at about 1/7 the rate of someone standing still. Push that to 99.9%, and the effect becomes even more extreme. For the travellers, the journey might feel like a few months while decades pass for those they left behind. The reason you can't just keep accelerating until you hit light speed is tied to energy. According to relativity, as an object with mass moves faster, its kinetic energy increases in a way that also increases its relativistic mass. Not its rest mass, which stays the same, but the amount of energy it carries, which behaves like extra mass. The faster you go, the more energy it takes to keep increasing your speed. As you approach the speed of light, the energy required skyrockets toward infinity. To actually reach light speed, you would need infinite energy. and infinite energy is not something the universe has on offer. This is why only massless particles like photons can travel at light speed. They are born moving at this pace and have no rest mass to slow them down. Anything with mass, a person, a planet, a pebble, must stay below that limit. It's not a matter of engineering around it. It's a fundamental law of how space-time operates. The speed limit is not arbitrary, nor is it imposed by some hidden barrier you could smash through with enough force. It is simply how reality is built. When we measure the speed of light, we're not just learning about light, we're learning about the maximum rate at which cause and effect can travel. In a universe without such a limit, events could influence each other instantly across any distance, and the sequence of cause and effect could break down entirely. The speed limit preserves the logical structure of the cosmos, keeping time flowing in one direction and ensuring that before and after remain meaningful concepts. Seen in this way, the speed of light is not an inconvenience holding us back from the stars. It is the quiet guardian of the universe's order, woven into the geometry of reality itself. It tells us that while we can go fast, we can never go infinitely fast, and that time and space are always dancing in step, no matter how hard we try to outrun them. If you were to ask why light travels at exactly 299,792,458 meters per second, you might expect the answer to be something like, because that's just how fast photons happen to go. But the real explanation is far more elegant, and it has nothing to do with light choosing a speed and everything to do with the properties of the universe itself. In the mid-19th century, the Scottish physicist James Clerk Maxwell developed a set of equations that brought electricity and magnetism together into a single theory: electromagnetism. Before Maxwell, scientists knew that electric charges could create electric fields, that magnets could create magnetic fields, and that changing one could influence the other. What Maxwell showed was that these effects were not just related, they were different faces of the same phenomenon. Maxwell's equations predicted that if you disturbed an electric field, it would create a changing magnetic field. That changing magnetic field, in turn, would create a changing electric field. This back and forth interaction could sustain itself, rippling through space as an electromagnetic wave. And when Maxwell calculated the speed at which these waves would travel, he found something astonishing. The number that fell out of the mathematics matched the measured speed of light. This was no coincidence. It meant that light itself is an electromagnetic wave, a self-propagating disturbance in the electric and magnetic fields that permeate the universe. And the speed of those waves depends entirely on two fundamental constants: the electric permittivity of free space, which describes how electric fields interact with the vacuum, and the magnetic permeability of free space, which describes how magnetic fields interact with it. Multiply those constants together in just the right way, and you get the inverse square root that defines the speed of electromagnetic waves. No matter whether you're talking about visible light, radio waves, X-rays or gamma rays, they all travel at the same speed in a vacuum, because they are all manifestations of the same underlying fields. The speed is not a property of the waves themselves, but of the medium they travel through, and in this case that medium is the vacuum of space-time. This is why the speed of a light is not arbitrary. Change the vacuum's permittivity or permeability, and the speed of light would be different. But those constants are themselves part of the deep structure of reality. They're not adjustable knobs we can turn. They're woven into the way space and time behave. In a sense, the speed of light is a fingerprint of the universe's physical laws. It is also worth noting that speed of light can be a misleading phrase. What we're really talking about is the speed at which any massless influence can travel, the ultimate speed limit for the transmission of information and energy. Light happens to be the most familiar example, but gravitational waves, hypothetical massless particles, and even the effects of electric and magnetic fields themselves all share the same constant speed in a vacuum. When you look at it this way, the magic number is not about light racing as fast as it can. It is about the vacuum itself setting the pace for how disturbances can move through it. Light travels at that speed because it is part of a perfectly balanced handshake between electricity and magnetism, a balance determined by the very fabric of space-time. And perhaps the most beautiful part is this. You can, in principle, derive the speed of light without ever observing light at all. Measure how electric and magnetic fields behave in empty space, and the number appears naturally from the mathematics. It is as if the universe has this rule quietly written into its operating manual, long before any stars began shining to give it a name. At everyday speeds, time feels wonderfully dependable. A second is a second whether you're walking, driving, or even flying on a plane. But this sense of stability is a quiet illusion, one that begins to unravel as you push closer to the speed of light. Special relativity tells us that time itself is not absolute, and that the faster you move through space, the more slowly you move through time. This phenomenon, known as time dilation, is not just a mathematical quirk. It has been measured, tested, and confirmed countless times. When you approach light speed, your clock, whether it is a wristwatch, a heartbeat, or the ticking of atoms, runs more slowly compared to someone who is stationary. For you, nothing feels unusual. Your thoughts, movements, and conversations happen at a perfectly normal pace. But for an outside observer, you are living in slow motion. To make sense of this, it helps to remember that in relativity, space and time are woven together into space-time. Moving faster through space means you must move slower through time to keep the total speed through space-time constant. It is not that your clock is broken, it is that you are genuinely experiencing less time than someone else between the same events. One of the most famous illustrations of this idea is the twin paradox. Imagine identical twins, Alice and Ben. Alice stays on Earth, while Ben boards a spaceship capable of travelling at 99% of the speed of light. He sets off on a journey to a distant star and back. For Ben, the trip might take only a few years according to his onboard clock. But when he returns, he finds that far more years have passed for Alice back on Earth. She has aged perhaps decades, while he has aged only a fraction of that time. The paradox is not really a contradiction. It comes from the fact that Ben's journey involves acceleration and deceleration, which breaks the symmetry between the two twins' experiences. Relativity predicts this exact outcome, and experiments with extremely accurate atomic clocks have shown that even tiny differences in speed can create measurable differences in elapsed time. Time dilation is not just a theoretical curiosity. It plays a role in the survival of certain particles. Muons, for instance, are unstable subatomic particles created when cosmic rays strike Earth's atmosphere. At rest, a muon's average lifetime is about 2/millionths of a second. At that rate, even moving at high speeds, they should decay long before they can reach the surface of the Earth. And yet, we detect muons at ground level all the time. The reason is that these muons are travelling at speeds close to the speed of light. From our perspective, their internal clocks are running much more slowly than they would at rest, allowing them to survive far longer than expected. In their own frame of reference, they still decay after just 2/millionths of a second. But from our point of view, that brief lifetime stretches out, giving them enough time to make the journey. This is one of the most direct and dramatic confirmations of time dilation in the natural world. Perhaps the most mind-bending consequence of time dilation is the idea that, for a photon, a particle of light, time does not pass at all. Travelling at light speed, the interval between emission and absorption is, from the photon's perspective, instantaneous. There is no before or after in the way we experience it. Of course, photons do not have conscious experiences, but it is still remarkable to think that the universe's fastest messengers are, in a sense, timeless. For humans, this effect remains firmly in the realm of extreme speeds. Even the fastest spacecraft we have built crawl along at a tiny fraction of the speed of light, so the time dilation they experience is negligible. But if one day we develop propulsion systems capable of pushing a crew to a significant fraction of light speed, their journeys will play out very differently in the timelines of those who stay behind. For the travellers, distant stars could be reached within a lifetime, even if centuries pass back home. There is a quiet poetry in this, the idea that speed can become a form of time travel, not into the past but into the future. Moving quickly enough through space lets you leap ahead in time relative to others, simply because your own clock has been ticking more slowly. This is not magic. It is the natural geometry of space-time revealing itself. Time dilation challenges the way we think about the present moment. It tells us that now is not a universal slice through the cosmos, shared equally by all observers. Instead, each of us carries our own private timeline, shaped by how we move and where we are. At ordinary speeds, these differences are too small to matter, but as you approach the cosmic limit, they grow into gaps you could drive a spaceship through, quite literally. It's tempting to think of time as a river flowing steadily forward, the same everywhere. But relativity shows us that the river's flow depends on the path you take through the landscape of space-time. For the fastest travellers, that river runs slower, and the view from their banks is unlike anything we can experience standing still. And while we may never move at light speed ourselves, knowing that the rules of time are this flexible makes the universe feel all the more extraordinary. When Albert Einstein published his special theory of relativity in 1905, one of its most famous consequences was the equation E equals mc squared. It is one of the most recognizable formulas in all of science, even among people who could not explain exactly what it means. Yet behind its simplicity lies a profound statement about the nature of reality. Mass and energy are not separate things. They are different forms of the same underlying entity, and they can be converted from one into the other. In that equation, E stands for energy, M stands for mass, and c is the speed of a light in a vacuum. That enormous number of 299,792,458 meters per second. Squaring c makes it unimaginably large. The implication is staggering. Even a tiny amount of mass contains a colossal amount of energy. A paperclip's worth of mass, fully converted into energy, could release enough power to light a city for days. This is not just a curiosity. It explains why nuclear reactions in stars or in reactors release so much energy. In nuclear fusion, light nuclei combine into heavier ones, and in the process, a small fraction of their mass is lost. That missing mass has not vanished. It has been transformed into energy, carried away by light, heat, and other particles. The same principle drives nuclear fission, where heavy nuclei split apart and again lose a tiny fraction of their combined mass, turning it into a burst of energy. But the equation also tells us something about speed limits in the universe. Massless particles, such as photons, are born travelling at the speed of light because nothing in their nature resists it. They have no rest mass, so they do not need to spend any energy accelerating from a standstill. In a sense, they do not have a choice. The structure of space-time dictates that if you are massless, you must move at c through the vacuum. For particles with mass, the story is different. Mass gives an object inertia, the resistance to changes in motion. The faster you try to move, the more energy you must put in to keep accelerating. And here is where relativity steps in with its most uncompromising rule. As you approach the speed of light, the amount of energy required to go even a little faster climbs toward infinity. You could pour the entire energy output of all the stars in the galaxy into your spaceship and still never quite reach C. Why does this happen? It is not that the object's rest mass is changing. That remains constant, but its total energy increases with speed, and in relativity, energy and mass are interchangeable. That extra energy behaves as if it were extra mass, making the object harder and harder to accelerate. The faster you go, the more your own energy works against you, as if the universe were quietly tightening the screws with every fraction of c you approach. This is why the cosmic rulebook separates the travellers into two distinct classes. Massless particles live entirely at c, experiencing no passage of time from their own perspective. Massive particles like you and me are bound to travel below C forever. We can flirt with it, draw as close as we like, but never cross the boundary. And there is no bridge between the two. You cannot take a photon and slow it to a stop in empty space, and you cannot take a proton and speed it up to the speed of light. The laws of physics do not allow a ticket between those clubs. There is a kind of elegance in this divide. Massless particles are the universe's messengers, carrying information and energy across vast distances with perfect fidelity to the cosmic limit. Massive particles are the architects of structure, able to slow, stop, and form the atoms, planets, and galaxies we see around us. Each plays its part in the grand design, and the speed of light is the line that defines their roles. This relationship between mass, energy, and the speed of light also helps explain why C appears in places you might not expect. It is not only about the motion of photons. C shows up in the equations of electromagnetism, in gravitational wave physics, and even in the structure of space-time itself. It is a conversion factor between different aspects of reality, as fundamental as the relationship between the number of seconds in a minute or the number of meters in a kilometer, but woven into the geometry of the cosmos. If you think of the universe as a vast interconnected system, E equals mc squared is one of its most concise pieces of code. It tells you that the energy bound up in matter is enormous, that speed and mass are deeply entangled, and that there is a limit to how fast anything with substance can go. It also reveals why the speed of light is not merely a quirk of photons, but a direct consequence of the relationship between mass and energy. Every time you see light streaming from the sun, or watch an image sent back from a distant spacecraft, you are watching mass and energy in perfect partnership. The sun's light began as mass in its core, fused into new elements and released as energy that sped across space at sea, bringing warmth and clarity to our tiny corner of the galaxy. That partnership has been in place for over 4 billion years, and it will continue for billions more, quietly following the rules set down in that deceptively simple equation. In the end, the cosmic rulebook is not written in complicated language. It is written in the balance between what has mass and what does not, between what can rest and what must always move, and in the middle of it all is the speed of light, the constant that ties energy to matter and keeps the universe running exactly as it does. When people hear the speed of light, they often imagine it as something exclusive to photons, as if only light gets to travel at this special pace. But in reality, the speed of light in a vacuum is not just a speed for light. It is the universal limit for any massless traveller, no matter what form it takes. Anything without rest mass, and without anything in its nature to slow it down, moves at exactly this speed through the fabric of space-time. One of the most spectacular examples is gravitational waves. Predicted by Einstein's general theory of relativity in 1916, these waves are ripples in the geometry of space-time itself, produced when massive objects accelerate, especially when they do so violently, like black holes colliding or neutron stars spiraling into each other. For a century, gravitational waves were purely theoretical. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected them directly for the first time. The event they observed was extraordinary. 2 black holes, each dozens of times more massive than the Sun, merging over 1 billion light-years away. The collision sent out gravitational waves that spread across the cosmos, distorting space and time as they passed. When they reached Earth, they had stretched and squeezed space by less than the width of a proton. But LIGO's incredibly precise instrument still recorded the signal, the speed at which these waves travelled, exactly the speed of light in a vacuum, matching photons step for step. This wasn't just a coincidence. Relativity predicts that gravitational waves must move at c, because they carry information about changes in the gravitational field, and no information can travel faster than this universal limit. Gravitational waves are remarkable not only for their speed, but for their persistence. Light can be blocked, scattered, or absorbed by matter, but gravitational waves pass through almost everything without slowing down. That means they can bring us news from parts of the universe light cannot easily reach, such as the inner workings of a black hole collision. Yet even these cosmic messengers, capable of crossing the universe largely unimpeded, are still bound by the same speed limit as light itself. Beyond gravitational waves, there are other theoretical travellers that would, if they exist, share the same relentless pace. One candidate is the graviton, a hypothetical quantum particle that would mediate the force of gravity in a quantum theory of gravity in the same way that photons mediate electromagnetism. If gravitons exist, they would be massless and therefore would travel at the speed of light. While no graviton has been detected, their properties are built into many theoretical models, and their speed is not negotiable under the rules of relativity. Another is the gluon, which carries the strong nuclear force. Gluons are indeed massless in theory, but unlike photons or hypothetical gravitons, they never roam freely through space. They are confined inside protons, neutrons, and other particles due to the peculiar nature of the strong force. Still, if a gluon could be isolated in empty space, it would travel at sea. The same applies to the photon's cousins in the realm of quantum theory, particles like the hypothetical axion, which is sometimes proposed as a candidate for dark matter. If massless, these two would join the lightspeed club. Then there is the neutrino, a particle once thought to be massless but now known to have a tiny non-zero mass. In the early days of neutrino research, it was assumed they zipped along at light speed, and they still come very close. Travelling at nearly c, neutrinos stream through the universe in vast numbers, passing through planets, stars, and people with barely a whisper of interaction. But their small mass means they fall just shy of the cosmic limit, proving again how strictly that boundary is enforced. The shared speed of these very different phenomena, light, gravitational waves, and any truly massless particle, comes from the same principle. In relativity, c is not just a property of photons, it is the maximum rate at which any cause can produce an effect. It is built into the structure of space-time itself. If something has no mass, it has no way to slow down, no rest frame to speak of, and no option but to travel at this exact pace. It's also worth noting that this speed is not something these travellers work to achieve. They are not accelerating to reach it, they are simply born and moving at it. A photon created in the core of a star emerges already at light speed, and will maintain that pace until it is absorbed. A gravitational wave generated in a cosmic collision emerges from the event horizon, already stretching and squeezing space-time at c. There is no ramp up, no hesitation, they exist only in motion, and that motion is always the same. Thinking of the speed of light in this way changes the perspective. Rather than imagining it as how fast light goes, it becomes how fast the universe allows any massless influence to travel. It is the single rate at which the geometry of space-time permits information to move, whether that information comes in the form of a ripple in gravity, a flash of light, or a particle so elusive we have yet to prove it exists. In the grand scheme, this makes the speed of light less about light itself, and more about the rules of reality. The fact that such different messengers, born from such different events, all share the same immutable speed is one of the most elegant signs that the universe is governed by deep underlying symmetries. And as far as we know, nothing can ever join their ranks unless it is willing to give up its mass entirely. A steep price for a ticket to travel at the fastest pace the cosmos will ever allow. From time to time, astronomers talk about objects or signals that appear to be moving faster than light. Headlines might announce a superluminal jet streaking from a galaxy's core, or scientists might describe a wave crest that seems to outrun the universe's ultimate speed limit. It can sound as though Einstein's cosmic rulebook has been broken, but in every confirmed case, the speed of light emerges unscathed. The apparent violations are illusions born from perspective, geometry, and the quirks of wave behaviour. One of the best-known examples comes from radio astronomy, in the form of relativistic jets. These are narrow beams of particles and radiation launched from the regions around supermassive black holes at the centres of galaxies. The particles in these jets are travelling at speeds close to the speed of light, but never exceeding it. Yet when astronomers observe them from Earth, the jets can appear to be moving faster than light across the sky. This strange effect is the result of a perfect alignment of speed and viewing angle. Imagine a jet angled slightly toward us, travelling at nearly the speed of light. Because it is moving almost directly in our direction, the light it emits at different points along its path takes progressively less time to reach us than you might expect. The jet covers a huge distance in space during the same period that its light is also closing the gap to us, making its apparent motion across the sky seem faster than light. In reality, the particles in the jet never break the limit. It is our perception, compressed by timing and geometry, that creates the illusion. A different sort of superluminal trick comes from the world of waves, where the concepts of phase velocity and group velocity can play mind games with our intuition. The phase velocity of a wave is the speed at which individual wave crests or troughs move. In some cases, such as in certain materials or in cleverly engineered signals, the phase velocity can be greater than the speed of light. But phase velocity does not represent the speed of any actual particle or signal carrying information. It is a mathematical description of how the shape of the wavefront moves, and that shape can shift faster than c without transmitting anything physical at that speed. Group velocity, on the other hand, is the speed at which the overall shape of a wave packet, the envelope containing a pulse, moves. This is usually the speed that corresponds to the transmission of information or energy. In most normal circumstances, group velocity is less than or equal to the speed of light. However, under very specific conditions, such as in materials that strongly absorb or distort light, group velocity can appear to exceed c, or even become negative, meaning the peak of the pulse seems to exit before it enters. While it sounds like science fiction, this is not a case of sending a message into the past. The faster-than-light group velocity is a result of reshaping the pulse in a way that shifts its peak forward without any part of the actual signal outrunning light. Astronomy offers yet more examples of apparent superluminal effects that turn out to be harmless to relativity. Take shadows, for instance. If you project a shadow onto a distant surface and sweep your hand across a light source, the edge of the shadow can move across the surface faster than the speed of light, given a large enough distance, but nothing physical is travelling along the surface. The shadow is just the absence of light, and the change in its position is not transmitting any information or matter faster than c. Similarly, a laser beam swept across the moon could have its spot move faster than light across the lunar surface. But again, no physical thing is moving between those 2 points at that speed. Even in the vast structures of the cosmos, we see what appear to be faster-than-light movements. Patterns in pulsars, fluctuations in the cosmic microwave background, and the sweeping arcs of certain radio signals can give the impression of speeds beyond the limit. But in every case, the trick lies in the distinction between the motion of a pattern and the motion of something carrying information. Relativity's limit applies only to the latter. The underlying reason nothing actually breaks the cosmic speed limit is that c is not about the speed of a thing we can chase. It is about the maximum rate at which cause and effect can be linked. You cannot send a signal, transmit energy, or push an object faster than c without tearing up the very structure of space-time. The apparent superluminal motions we observe never actually involve a cause and effect relationship that skips ahead of light. They only create the impression of it when viewed from a particular angle, or through the behaviour of a wave pattern. In a way, these illusions are a testament to the creativity of the universe. It plays with perspective and physics in ways that keep us on our toes, reminding us that the cosmos is as much about how we see as it is about what is actually there. Light's speed limit remains intact, but there is still plenty of room for mischief in the details. Whether it is a jet from a black hole leaning toward us just so, a wave crest outpacing its own information, or a shadow racing across a planet's surface, The universe gives us glimpses of what faster than light might look like, while making sure the real thing never quite happens. If you look far enough into the universe, you will find galaxies that appear to be racing away from us faster than the speed of light. At first glance, this seems like a clear violation of the cosmic speed limit. How can anything move that fast without breaking Einstein's rules? The answer lies in a subtle but crucial distinction. There is a difference between objects moving through space and the fabric of space itself expanding. In everyday life, space feels like an empty backdrop against which things move. A car drives down a road, a plane flies through the air, a boat sails across the sea. In each case, the object is moving through a medium, and the speed of light acts as a hard limit on that motion. But space in cosmology is not just a passive stage, it is dynamic. It can stretch, bend, and curve, and when it stretches, it carries everything embedded in it along for the ride. The idea that the universe is expanding came from the work of Edwin Hubble and others in the early 20th century. Observing the light from distant galaxies, Hubble found that their spectral lines were shifted toward the red end of the spectrum, a redshift. The farther away the galaxy, the greater the redshift. This pattern could be explained if the space between galaxies was increasing over time, stretching the light waves as they travelled. This discovery transformed our view of the cosmos, revealing that the universe is not static, but growing. In an expanding universe, distant galaxies are not so much racing away from us through space as they are being carried away with space. Imagine a loaf of raisin bread rising in the oven. The raisins are like galaxies, and the dough is like space itself. As the dough expands, every raisin sees all the other raisins moving away, and the farther apart two raisins are, the faster they recede from each other. No raisin is travelling through the dough at high speed. The dough is simply stretching, increasing the distances between all of them. This means there is no contradiction when some galaxies appear to recede from us faster than light. They are not moving through space at superluminal speeds. The space between us and them is expanding so quickly that the total separation grows by more than a light year each year. This kind of motion is not limited by relativity's speed cap because relativity applies to movement through space, not to the rate at which space itself changes. There is an important consequence of this stretching. It defines a cosmic horizon. Light from galaxies beyond a certain distance will never reach us, no matter how long we wait, because the space between us and them is expanding faster than the light can cover it. It is as though the river of space is flowing so quickly that a swimmer, in this case a photon, can never reach the shore. This horizon marks the limit of our observable universe, a bubble inside which light has had time to reach us since the Big Bang. On smaller scales, gravity can hold things together against the expansion of space. The Milky Way is not being torn apart, and neither is our local group of galaxies. The expansion is negligible at these scales because the gravitational bonds are much stronger. Space is stretching, but local forces can counteract it. It is only over vast intergalactic distances that expansion dominates. The most extreme form of cosmic expansion is thought to have occurred in the first fraction of a second after the Big Bang, during a period called inflation. In this era, space expanded exponentially, doubling in size over and over at a rate that would have made even light seem sluggish. Inflation ended long before galaxies formed, but its legacy remains imprinted in the large-scale structure of the cosmos and in the faint afterglow of the Big Bang, the cosmic microwave background. Today, the expansion of the universe is not only continuing but accelerating, driven by what we call dark energy. We do not yet know exactly what dark energy is, but it acts as a kind of anti-gravity, causing the stretching of space to speed up. If this acceleration continues indefinitely, more and more galaxies will slip beyond our cosmic horizon, disappearing from view as their light becomes too redshifted to detect. In the far future, distant galaxies will vanish from the night sky, not because they have gone anywhere in a conventional sense, but because the space between us will have grown too fast for their light to ever arrive. Understanding the difference between motion through space and the expansion of space itself is one of the keys to making peace with these faster-than-light appearances. Galaxies can be pulled apart by the stretching of space at any rate, but no spaceship, photon, or gravitational wave can ever outrun the local rules of relativity. The universe is not breaking its own laws. It is just applying them in ways that our everyday experience does not prepare us for. It is a little like standing on an escalator that speeds up as you ride. If you are walking along the escalator, your walking speed is limited by your own stride, but the escalator's motion adds to your overall progress. Space is the moving escalator, galaxies are the passengers. From the right vantage point, it can look as though some passengers are moving impossibly fast, but it is really the floor beneath them that is carrying them along. In this way, the cosmic expansion gives us a universe where light's speed limit is preserved locally, while the vastness of space still allows for breathtaking separations on the grandest scales. It is one of those moments where the laws of physics do not so much forbid as they redefine what is possible, reminding us that the universe is under no obligation to behave in ways that feel familiar. In the early days of quantum mechanics, Albert Einstein admired much about the new theory, but he had a persistent unease about one of its stranger predictions. Along with Boris Podolsky and Nathan Rosen, he explored a scenario that would later become known as the EPR paradox. In it, two particles could become linked in such a way that measuring one would instantly reveal something about the other, no matter how far apart they were. Einstein famously called it spooky action at a distance, and he did not mean that as a compliment. This phenomenon is now called quantum entanglement, and experiments have shown it is very real. When two particles are entangled, their properties are correlated in a way that cannot be explained by each particle carrying its own preset instructions. Instead, it is as though the two particles share a single quantum state. If you measure one particle and find, for example, that it has spin up, the other particle's spin will be found to be spin down, even if the two are separated by light years. The change in our knowledge about the second particle happens instantaneously in our description of the system. At first glance, this sounds like faster-than-light communication. Measure particle A and particle B knows instantly what result it should give. But this is where quantum mechanics keeps its secrets. Entanglement does not let you send a message faster than light, because you cannot control the outcome of your measurement on particle A. Quantum measurements are inherently probabilistic. You can measure spin along a chosen axis, but the result, up or down, is random. All entanglement guarantees is that the other particle's measurement will match the correlation predicted by quantum theory. This randomness is the key to why relativity remains safe. Imagine you and a friend share a pair of entangled particles, and you're on opposite sides of the galaxy. You decide to measure yours, hoping to send a 1 if you get spin up and a 0 if you get spin down. You have no control over which one you get, so you cannot actually encode a meaningful message. Your friend's measurements will produce a random string of 1s and 0s too. Only when you later compare results, using lightspeed communication, will you see the perfect correlation. In essence, entanglement changes what we know about a system, not what is physically sent from one place to another in real time. No usable information, no matter how cleverly you try to disguise it, can leap ahead of light's limit this way. The instantaneous change is not a signal travelling faster than c, but a shift in the description of the shared quantum state. Physicists have tested this idea with increasing sophistication, closing loopholes and pushing the distances involved. In 2017, Chinese scientists used a satellite named Mishus to create entangled photons and send them to ground stations over 1,200 kilometers apart. The correlation still held, but no faster-than-light messages were transmitted. The rules of quantum mechanics and relativity worked in perfect harmony. Weird, yes, but law-abiding. The idea can still feel unsettling. In our everyday world, we expect causes to precede effects in a nice, orderly chain, connected by something moving from one point to another. Entanglement seems to bypass that chain entirely. It is tempting to picture one particle instantly telling the other how to behave, but in quantum theory, the particles are not really separate in the way we imagine. They are parts of a single, non-local system. The correlations are built into the state itself, not transmitted from one place to another at the moment of measurement. Some interpretations of quantum mechanics try to make this more palatable. In the many worlds view, for example, measuring one particle does not change the other at all. It simply reveals which branch of reality you are now in, and in that branch, the other particle's state is already consistent. Other interpretations, like Bohmian mechanics, keep the idea of hidden variables, but allow for non-local influences that do not carry signals. None of these approaches allow for faster-than-light messaging, they just offer different mental pictures of the same mathematics. Entanglement has practical uses, but they all respect the cosmic speed limit. Quantum key distribution, for instance, can use entanglement to generate encryption keys that are provably secure against eavesdropping. If someone tries to intercept or measure the particles in transit, the disturbance will be detectable, but even here, you still need ordinary light-speed communication to compare parts of the key and verify its integrity. Perhaps the most remarkable thing about entanglement is that it expands our understanding of connection without undermining the structure of space-time. It tells us that the universe allows correlations that seem almost magical. Yet these correlations fit neatly within the broader laws that govern motion, energy, and causality. The spooky part is not that information is racing faster than light, but that the universe permits such perfect alignment between things that can be unimaginably far apart. Einstein's discomfort with entanglement was never fully resolved in his lifetime, but today, what he saw as a flaw has become one of the most celebrated features of quantum mechanics. It is a reminder that reality can be stranger than our instincts predict, and that the speed of light is not just a barrier, but a framework within which even the strangest phenomena still find their place. For most of human history, gravity was thought of as an instantaneous force. In Isaac Newton's time, the idea that every mass pulled on every other mass was accepted without worrying about how quickly that pull might travel. In Newton's equations, gravity acted across space with no delay, as though the universe were a perfectly rigid structure, where a change in one place could be felt everywhere else at once. It worked beautifully for predicting planetary orbits, but it left an uncomfortable question. How could the influence of gravity leap across the cosmos instantly? In the early 20th century, Einstein's general theory of relativity reframed the picture entirely. Gravity was no longer a mysterious force acting at a distance. Instead, it was the warping of space-time itself by mass and energy. Planets orbit stars not because they are pulled in the Newtonian sense, but because they are following the curved paths laid out by space-time around massive bodies. In this new framework, changes in a gravitational field, say if a star moves, cannot be communicated instantaneously. They must travel outward as ripples in space-time, known as gravitational waves. And relativity is clear about their speed. They move at exactly the speed of light in a vacuum. This means that if, in some cosmic drama, the sun were to suddenly vanish, a thought experiment that physicists use with care, Earth would continue orbiting the empty point where the sun had been for about 8 minutes. That is the time it takes light, and therefore gravity's influence, to travel from the sun to Earth. There would be no sudden jolt, no instant correction to our orbit. The information that the sun was gone would arrive as a gravitational disturbance moving at sea. For decades we had no direct way to measure gravity's speed. Astronomers could put constraints on it by studying the behaviour of planets and the timing of signals from pulsars, but the precision was limited. What we needed was a way to detect gravitational waves directly and compare their arrival to that of light from the same event. That opportunity finally came in 2015, when the LIGO Observatory made its historic first detection of gravitational waves from a pair of merging black holes. While that confirmed the existence of the waves themselves, black hole mergers don't produce visible light for us to compare. The real test would require a cosmic event loud enough in both gravity and light. That test arrived on August 17, 2017. Astronomers around the world watched as LIGO, and its European counterpart Virgo, picked up a distinctive chirp signal from two neutron stars spiraling together more than 130 million light-years away. Neutron stars are the dense remnants of massive stars, each packing more mass than the Sun into a sphere barely the size of a city. As they circle each other at incredible speeds, they send out powerful gravitational waves that increase in frequency as the stars draw closer, right up to their collision. Just 1.7 seconds after LIGO registered the peak of this gravitational wave signal, telescopes detected a flash of gamma rays from the same region of space, the telltale sign of the neutron stars' merger. The difference in arrival times was astonishingly small, given the immense distance the signals had travelled. Over 130 million years, gravity and light had raced across the cosmos and arrived almost simultaneously. That 1.7-second gap is easily explained by the astrophysics of the merger. The gravitational waves were generated in the final moments of the neutron star's dance, while the gamma-ray burst came from the energetic jet that blasted out shortly after the collision. The fact that the two signals arrived so close together tells us that the speed of gravity is equal to the speed of light to an extraordinary degree of accuracy, differing at most by a few parts in a quadrillion. This result was a triumph for both relativity and observational astronomy. It confirmed that gravitational waves do indeed travel at sea, just as Einstein predicted, and it closed the door on many speculative theories that had proposed otherwise. If gravity had been even slightly slower or faster than light, the difference would have been obvious after such a long journey. Instead, the match was perfect within the limits of our measurements. The beauty of this finding is that it reinforces the unity of the universe's laws. Light and gravity are very different phenomena. One is an electromagnetic wave, the other a ripple in space-time itself, yet they share the same ultimate speed because they are both governed by the geometry of space-time. That speed is not an accident of the particles involved, but a fundamental feature of the stage on which the cosmic drama unfolds. Gravitational wave astronomy is still in its infancy, but already it has given us this profound confirmation of nature's consistency. In the years ahead, as detectors become more sensitive and more events are observed, we will have even more opportunities to test the speed of gravity and watch it perform in real time. For now, we can say with confidence that when the universe speaks through its two great messengers, light and gravity, they keep perfect time with each other, no matter how far they have to travel. When we say that light travels at 299,792,458 meters per second, we are talking about its speed in a perfect vacuum, an environment utterly empty of matter. But in the real world, light rarely has the luxury of such unobstructed travel. It is constantly passing through air, water, glass, or other materials, and in these media, light slows down, not by a small margin either. In water, light moves at about 3/4 of its vacuum speed, and in glass it can slow to roughly 2/3. At first glance, this can seem puzzling. If the speed of light is supposed to be a cosmic constant, how can it change just because it is passing through a different substance? The answer is that the fundamental constant, the speed of light in a vacuum, is still the same. What changes is how light interacts with the medium it is travelling through. Light is an electromagnetic wave, and when it enters a material, it interacts with the charged particles in that material, especially the electrons. These interactions cause delays. Photons are absorbed by atoms, which then re-emit them, or they are scattered in ways that slightly shift their paths. The process is incredibly fast, but it is not instantaneous. The result is that, on average, the wavefront of light takes longer to pass through the material than it would through empty space. This slowing down is described by a quantity called the refractive index, which tells us how much the speed of light is reduced in a given material. A refractive index of 1 means light travels at full vacuum speed. Air has a refractive index just over 1, so the effect is barely noticeable. Water has an index around 1.33, and typical glass ranges from about 1.5 to 1.9, depending on its composition. The change in speed also changes the light's direction when it passes from one medium to another. an effect known as refraction. You have seen this many times. A straw in a glass of water appears bent at the surface, or a pebble under a stream looks closer to the surface than it really is. When light enters a medium where it travels more slowly, it bends toward the normal, the imaginary line perpendicular to the surface. When it leaves for a faster medium, it bends away from the normal. This bending is not just a curiosity, it is the principle behind lenses, prisms, and much of our optical technology. Lenses work by carefully shaping transparent materials so that refraction bends light rays to meet at a single point, forming a sharp image. In a camera, a convex lens focuses light from a scene onto a sensor. In your eye, the cornea and lens work together to focus light onto the retina. Without refraction, the world would be a blur, and photography, telescopes, and eyeglasses would not exist. Prisms take refraction in another direction, literally. Because the refractive index of a material can depend on the wavelength of light, different colours slow down by slightly different amounts. This is called dispersion. In most transparent materials, shorter wavelengths, like blue and violet light, are slowed more than longer wavelengths, like red. When white light enters a prism, each colour bends by a different amount, spreading into a spectrum. Isaac Newton famously used a prism to show that white light is made of all the colours of the rainbow, each refracted by a different angle. Nature puts on its own prism show in the form of rainbows. When sunlight enters a raindrop, it slows and refracts, bending toward the normal. Inside the drop, the light reflects off the back surface, then refracts again as it leaves. Dispersion during these two refractions separates the colours, and the millions of raindrops in the air combine to produce the sweeping arcs of colour we see. The angle of refraction is what determines the rainbow's position in the sky, and it is why the colours always appear in the same order. The slowing of light in a medium has another curious side effect. Under the right conditions, light can be slowed dramatically, even to a crawl. In certain laboratory setups using ultra-cold gases or specially prepared materials, scientists have reduced the group velocity of light pulses to just a few meters per second. This does not mean photons themselves have gained mass or abandoned their nature. It means the interactions inside the medium delay the progress of the light pulse's envelope to an extreme degree. In some experiments, light has even been stopped, for brief moments, by storing its energy in the atoms of a medium and then re-releasing it. Despite these dramatic variations, the underlying rule remains the same. In a vacuum, light always travels at c. The changes we observe in materials are the result of light constantly pausing to interact with the matter it passes through, adding tiny delays that accumulate over distance. It is like a runner in a crowded market. They may still be capable of top speed, but weaving around shoppers and stopping briefly at stalls makes the journey slower overall. The slowing of light is not a limitation to lament, it is a gift. Without it, refraction would not exist, lenses could not focus, and rainbows would never brighten a grey sky after rain. The way light dances with matter, bending, splitting and slowing, has given us tools to see the smallest cells in the most distant galaxies. It has painted the world in colours, given shape to our vision, and offered a window into the structure of reality itself. For more than a century, physics has been very clear about one thing. Nothing with mass can travel faster than the speed of light in a vacuum. That has not stopped human imagination from repeatedly poking at the rule, prodding it like a child testing the boundaries of bedtime. Science fiction is full of clever loopholes, warp drives, wormholes, hyperspace jumps, that all promise to sidestep the cosmic speed limit without actually breaking it. The question is, could any of these ideas work in reality? Or are they destined to remain comfortably in the pages of novels and the frames of films? The first contender is the warp drive, a staple of futuristic fiction. The most famous version, inspired by a concept proposed by physicist Miguel Alcubierre in the 1990s, is not about moving a ship faster than light through space, but about moving space itself. In this idea, You would contract space in front of your ship and expand it behind, effectively riding a wave of distorted space-time. Locally, you would not be travelling faster than light at all. You could sit inside your warp bubble sipping tea, but to an outside observer, you would appear to be crossing vast distances in far less time than light would take. It sounds almost sensible until you look at the details. Creating a warp bubble, according to Alcubierre's mathematics, would require enormous amounts of negative energy. Not just a lot, but potentially more than the total energy output of all the stars in the observable universe. Negative energy is not something you can order in bulk from a laboratory supply catalogue. While quantum theory allows for tiny amounts to appear fleetingly, sustaining enough to warp space-time for a practical journey remains far beyond anything we can even begin to engineer. And there's the little problem of what happens when you turn the bubble off. Some calculations suggest the energy release could be catastrophic, not exactly ideal for docking procedures. Then there is the wormhole, another favourite of science fiction. These hypothetical tunnels through space-time could, in theory, connect two distant points in the universe directly, allowing you to step through and arrive light years away without ever travelling faster than light locally. Wormholes are predicted as possible solutions to Einstein's equations of general relativity, and unlike warp drives, they do not necessarily require you to drag an entire bubble of space along with you. But wormholes have their own set of obstacles. A naturally occurring wormhole, if such a thing exists, would almost certainly be microscopic and collapse instantly. To hold one open, large enough for a human, you would again need negative energy to counteract the intense gravitational forces trying to close it. Even if you solved that problem, wormholes could be unstable in unpredictable ways. A sudden fluctuation could snap it shut while you're halfway through, which is not a scenario anyone wants to test. There is also the troubling issue of time travel. Some configurations of wormholes could allow you to arrive before you left, raising all sorts of causality headaches. Other ideas push the boundaries of physics in more exotic directions. Hyperspace, a concept beloved by science fiction writers, imagines an alternative dimension where the rules of distance and speed are different, allowing for rapid travel that appears faster than light when projected into our universe. While entertaining, hyperspace has no basis in established physics. It is more a narrative tool than a theoretical proposal. Some physicists have speculated about tachyons, hypothetical particles that always travel faster than light. If they exist, they would never slow down to light speed. For them, that would be like trying to come to a complete stop at infinity. But tachyons also introduce problems with causality, making it possible, in theory, to send information backwards in time. No experimental evidence for tachyons has ever been found, and most physicists suspect they are more a mathematical curiosity than a real feature of the universe. A different approach sidesteps speed entirely, and looks at manipulating the start and end points instead. If you cannot make the journey faster, perhaps you can bring the destination closer. Ideas like cosmic string shortcuts, involving incredibly dense, one-dimensional defects in space-time, hint at ways gravity itself might be used to bend the geometry of the universe in our favour. Unfortunately, we have never observed a cosmic string, and the energies involved in using one would be as daunting as any warp drive scheme. Underlying all these proposals is the stubborn reality of Einstein's special relativity. As you accelerate toward the speed of light, your energy requirement increases without bound. You cannot simply push harder and break through the barrier. The closer you get, the more space-time itself pushes back, like a runner finding the track tilting ever steeper beneath their feet. Any real-world attempt to go faster has to find a way to cheat not the speed itself, but the geometry that defines it. It is worth remembering that faster-than-light travel is not just a technological challenge, but a conceptual one. Many of the laws of physics as we understand them are built on the assumption that nothing outruns light. Break that rule, and you risk unravelling causality, making effects happen before their causes. That is not just awkward for storytelling, It threatens the logical consistency of the universe itself. This does not mean humanity will never find a way to cross the stars in less time than light would take. Our understanding of physics has changed dramatically in the past few centuries, and it will continue to evolve. But as of now, all credible paths to faster-than-light travel involve either unproven physics or energy requirements so immense they make building a starship seem like the easy part. For the foreseeable future, our dreams of hopping between distant stars in an afternoon will remain in the realm of imagination, and perhaps that is not such a bad thing. After all, limitations often spark creativity, and in the meantime, the universe has given us plenty to explore at sublight speeds, from the planets in our own backyard to the faint glow of galaxies billions of light years away. Imagine, for a moment, a universe where light does not exist. No warm glow of the sun, no gentle gleam of moonlight, no shimmering stars scattered across the sky. Without light, vision as we know it would never have evolved. Eyes would have no purpose. In fact, most of the life forms we are familiar with would not even make sense in such a world. Plants, for instance, rely on light for photosynthesis, turning sunlight into the energy that fuels almost every food chain on Earth. Without it, photosynthesis vanishes, and with it, the green anchor of almost all ecosystems. In this lightless universe, life might still exist, but it would be nothing like the life we know. Perhaps it would evolve deep underground or near geothermal vents, where heat and chemical reactions take the place of sunlight. There are already organisms on Earth, such as certain bacteria, that thrive without light, using chemical energy from minerals instead. Our imagined universe might be full of such chemotrophs, slowly feeding off whatever energy gradients they can find. Evolution would still have its playground, but the palette of possibilities would be far more limited and probably less colourful, literally. If we widen the thought experiment to remove not just light, but the universal speed limit that light represents, the consequences grow stranger. In our universe, the speed of light is woven into the very fabric of space and time. It is not just a property of photons, it sets the maximum speed at which any information or influence can travel. Without it, the structure of causality would be under siege. If signals could arrive before they were sent, events could be jumbled out of order. You might experience an effect before its cause, a deeply unsettling concept, and one that could make the universe a very unstable place. Astronomy, as a field, would not exist without light. Nearly everything we know about the cosmos comes from detecting electromagnetic radiation, not just visible light, but radio waves, infrared, ultraviolet, X-rays, and gamma rays. Without these messengers crossing the void, we would be left in almost total ignorance of the wider universe. Even if some other force could carry information, the lack of a finite travel speed for it would make mapping the cosmos meaningless. You could, in principle, know about events the instant they happen billions of light years away. While that might sound convenient, it would strip away one of the most fundamental aspects of cosmic history, the delay that lets us see the universe as it was, not just as it is. The night sky, of course, would be gone, or perhaps never born. Stars without light are not really stars in any recognizable sense. They might still burn internally, releasing energy in other forms, but without electromagnetic radiation, their presence would be undetectable except by whatever forces might still operate. The romance of gazing up at constellations, of tracing patterns in the heavens, would be replaced by a kind of infinite darkness. Our sense of place in the universe might never develop at all. In the realm of physics, removing light and its speed limit would tear apart much of what we understand about relativity. Einstein's theories hinge on the constancy of the speed of light for all observers. If that speed limit disappears, so too does the elegant structure of space-time, which binds together time and distance into a coherent whole. Time might lose its steady march, becoming more of a chaotic jumble, or perhaps it would cease to have meaning entirely. Without light's limit, there is nothing to prevent instantaneous connections across space, but that also means nothing to preserve the sequence of cause and effect. It is possible that, In such a universe, complex structures, from galaxies to living beings, might never arise, simply because the rules that allow order to persist are gone. For life, the lack of light would not just be a challenge for vision or photosynthesis, it would remove one of the most consistent environmental cues. On Earth, day and night cycles have shaped behavior for billions of years. Without any form of light to mark time, organisms might rely entirely on internal rhythms or environmental changes unrelated to astronomy. Sleep, as we know it, might never evolve, or it could be dictated purely by energy availability, not the turning of a planet beneath a star. The whole concept of a day would be meaningless. In such a universe, communication between living things would also be different. Light-based signals like the colours of flowers or the bioluminescence of fireflies would never emerge. Sound could still exist in a medium like air or water, and chemical signals might be more common, as they are for many organisms in Earth's dark environments. But the speed and reach of such signals would be vastly different from the near-instantaneous nature of light. Communication would likely be slower, more local, and perhaps more intimate, tied closely to physical proximity. It is tempting to imagine that such a universe would be simpler, but the truth is it might be far stranger. Without the unifying speed limit set by light, different parts of reality could be connected in unpredictable ways. You might tap a rock in one place and feel the vibration instantly 1,000 kilometers away, yet the same action might take a different amount of time somewhere else. Consistency, the bedrock of physics, would be difficult to maintain. Science itself, at least as we practice it, depends on regularity. The idea that the same experiment gives the same result under the same conditions. Remove light's constant speed, and even that assumption could crumble. Ultimately, our imagined world without light is a world without much of what gives our own universe its shape, order, and beauty. Life could still find a way, as it so often does, but it would be operating in a reality stripped of many of the tools and cues that have shaped existence on Earth. And without a speed limit to govern the spread of information and influence, the tapestry of cause and effect that underlies everything might fray beyond recognition. Thinking about this absence helps us appreciate just how much light, and the constant speed it represents, is not merely a convenience for human eyes, but a deep, structural feature of reality. It is the heartbeat of causality, the signal that threads through the story of the cosmos, and the quiet architect of so much of what we take for granted. Remove it, and you remove not just a feature of the universe, but its rhythm, its narrative, and perhaps even its ability to hold itself together at all. When you look out at the night sky, you are not seeing the universe as it is now. You are seeing it as it was, because light takes time to travel. The glow of the moon is just over 1 second old when it reaches us. Sunlight takes about 8 minutes to arrive. The nearest stars in our galaxy are seen as they were years ago, and the faintest galaxies captured by our most powerful telescopes are ancient messengers, their light having crossed billions of years of space to reach our eyes. This delay is not an inconvenience. It is a cosmic time machine. The speed of light sets the scale of what we can know, defining the observable universe. Even though the entire universe might be vastly larger, perhaps infinite, we are bound to a spherical bubble around us from which light has had time to reach us since the beginning of the cosmos. That bubble is about 46 billion light-years in radius. Anything beyond that, we cannot see it because its light simply hasn't had enough time to get here. That might sound straightforward, but the picture becomes stranger when you realize the universe has been expanding the whole time those photons have been traveling. Light that started its journey when the universe was young had to cross not just distance, but distance that was stretching underneath it. It is a bit like trying to run across a moving walkway, except the walkway is expanding in all directions and getting faster the farther away you are from home. This is why, despite being only about 13.8 billion years old, the observable universe is much larger in radius than 13.8 billion light-years. The speed of light also imposes an unyielding barrier on communication. Imagine a civilization living on a planet 100 light-years away. Even if both you and they had the technology to send instant, flawless signals, those signals would still take a century to make the trip. If you sent a message today, you would not get their reply until the year 2225, assuming they replied straight away and did not wait a century out of politeness. This means that cosmic diplomacy, if it exists, is glacially slow. The universe, for all its vastness, is stitched together with very patient conversations. Closer to home, this speed limit defines the boundaries of practical exploration. We can send probes to the outer planets within years or decades, but to reach even the nearest star would take tens of thousands of years with our current propulsion technology. That is not because we are unimaginative engineers. It is because the speed of light is so fast that even reaching a small fraction of it is immensely difficult. Space, it turns out, is big in a way our everyday intuition struggles to grasp. One of the more poetic aspects of light speed is that it gives the universe a narrative. Without it, everything would be visible instantly, and all events would be simultaneous from every perspective. There would be no cosmic history to uncover, no sense of depth in time. Instead, the universe tells its story gradually, like an ancient scroll unrolling, the earliest chapters faint and red-shifted, the newer ones crisp and bright. The delay is not a flaw. It is the reason we can study how galaxies evolve, how stars are born, and how the cosmic web has changed over billions of years. Of course, the same rule that lets us witness this grand history also means we will never directly observe certain things. If an event happens now beyond our observable horizon, no matter how dramatic, we will never know about it. Those regions of space are permanently beyond our reach, locked away by the finite speed of light and the relentless expansion of space. In a sense, every observer in the universe has their own personal cosmic bubble, their own horizon of knowable reality. This horizon also has practical consequences for the future. As the expansion of the universe accelerates, more and more distant galaxies will cross beyond it, their light stretched so far into the infrared that it becomes undetectable. Billions of years from now, a distant civilization might look up and see only the stars of their own galaxy, unaware that there was ever more to the universe than that. The cosmic stage will seem smaller, but only because the actors beyond the horizon have slipped away into an unreachable darkness. From a travel perspective, this all means that journeys to distant galaxies are not just difficult, they are impossible. Even if you could travel at the speed of light, some galaxies are receding so quickly due to the expansion of space that you could never reach them. The finish line is moving away faster than you can run. The speed of light is not just a rule about moving through space, it is a boundary on the very shape of what is possible. In human terms, these limits can feel frustrating. We are a curious species, and the idea that parts of the universe are forever off limits does not sit easily. But there is a certain comfort in knowing that this limit is also what makes the universe stable. Without it, causality could collapse, and the sequence of events that makes reality comprehensible would unravel. The speed of light is not just an arbitrary number, it is the cosmic stitching that holds the fabric of space-time together. So the next time you gaze up at the stars, remember that you are seeing not only distance, but time itself. The light from those points in the sky has been travelling at an unchanging, perfect pace, the same pace it has always kept, and it defines the shape of the universe you can know. Beyond that limit lies a reality you will never see, a reminder that, in the grand cosmic story, mystery is not just a gap in our knowledge. It is a built-in feature of the script. Imagine standing on a quiet hill under a clear night sky. The stars seem to go on forever, glittering in every direction. It is tempting to think that, given a good enough telescope, you could peer endlessly into the depths of space. But the truth is, there is a hard limit to how far we can see, a cosmic horizon that is as real and unyielding as the one you see over the ocean. This horizon is not a wall or a physical barrier, it is a limit set by time itself. The universe has not been around forever. It began about 13.8 billion years ago with the Big Bang. Since then, light has been racing across the expanding fabric of space to reach us. That means there is a maximum distance from which light could have travelled since the beginning of time, and anything beyond that remains invisible to us not because it is hidden, but because its light has not yet had time to arrive. At first glance, you might think that the farthest we can see is 13.8 billion light-years, matching the age of the universe. But that's not the whole story. While that light has been travelling toward us, space itself has been stretching. This expansion means the most distant objects we can observe are now about 46 billion light-years away. We are looking at them not as they are now, but as they were billions of years ago when the universe was young. The cosmic horizon is a time horizon as much as a distance one. Looking far away is also looking far back in time. In the faintest reaches of our view, we see not galaxies, but the afterglow of the Big Bang itself, the cosmic microwave background radiation. This faint bath of microwaves spread evenly across the sky is the oldest light we can detect. It was released about 380,000 years after the Big Bang, when the hot, opaque plasma of the early universe cooled enough for atoms to form and light to travel freely. Before that moment, the cosmos was a fog of particles scattering photons in every direction, making it impossible for light to pass unimpeded. What lies beyond that horizon is not necessarily empty. In fact, most cosmologists are confident the universe continues far beyond what we can see, perhaps infinitely far. But from our vantage point, those regions are hidden from us forever. It is not a matter of waiting long enough. The expansion of the universe ensures that some parts are moving away from us faster than light can bridge the gap. This is not breaking the cosmic speed limit. It is space itself expanding, carrying galaxies along like raisins in a rising loaf of bread. One of the most remarkable aspects of this horizon is that it is different for every observer. If you were standing in a galaxy 10 billion light-years from here, your observable universe would overlap with ours in some regions, but not all. There would be galaxies visible to you that no telescope on Earth could ever detect, and vice versa. Each observer in the cosmos has their own unique bubble of visibility, bounded by how far light has reached in their corner of the universe. The cosmic horizon is not static. It evolves with time. In the early universe it was much smaller, simply because less time had passed since the Big Bang. As billions of years went by, light from more distant regions had time to reach us, and our horizon expanded. But in the far future, cosmic acceleration will begin to shrink the number of galaxies we can see, even as the horizon itself still exists. Galaxies will cross it, disappearing from view as their light is stretched beyond detectability. This brings a bittersweet truth. The night sky is not eternal. Billions of years from now, the universe will appear emptier, not because galaxies are disappearing in any physical sense, but because they are receding beyond the reach of light. Civilizations in that distant future might see only their local group of galaxies, with no evidence of the broader cosmos. To them, the idea of a vast expanding universe might be as strange as the idea of a spherical Earth was to ancient people. Our ability to measure and map this horizon comes from a combination of clever observation and theoretical understanding. Telescopes like the Hubble and the James Webb Space Telescope peer deep into the past, revealing galaxies from when the universe was only a fraction of its current age. Instruments like the Planck satellite have mapped the cosmic microwave background in exquisite detail, showing tiny fluctuations in temperature that are the seeds of all the cosmic structure we see today. These observations give us a kind of cosmic archaeology, piecing together a timeline that stretches back almost to the very beginning. Standing here in our tiny corner of the cosmos, it is humbling to know that there are vast realms forever beyond our sight. The cosmic horizon is both a limit and an invitation, a reminder that the universe is bigger than our imaginations can hold, and that our picture of it will always be partial. Yet within that horizon lies everything we can know, everything we can measure, and everything that has ever influenced us. and in a way, that makes it precious. The light that reaches us from the edge of the observable universe has travelled for almost the entire history of time itself. Each photon is a survivor of a journey lasting billions of years, carrying with it a tiny piece of the universe's story. Together, they weave the grand tapestry we call the cosmos, and they stop exactly at our cosmic horizon. Every time you look at the night sky, you're not really seeing it as it is now. You're seeing it as it was. Light takes time to travel, and that means the cosmos presents itself to us not as a live broadcast, but as a vast collection of recordings, each star, galaxy, and glowing cloud telling a story from its own chapter of history. In a sense, astronomy is not so much about looking far away as it is about looking far back in time. Even the sun, that familiar ball of fire lighting our days, is an 8-minute-old memory. The sunlight warming your skin left the sun when whatever you're doing right now was just beginning. If the sun vanished this instant, don't worry, it's not planning to. We would continue to see it for over 8 minutes before the darkness and cold began to arrive. This built-in delay gets longer the farther you look. The light from the nearest star system, Alpha Centauri, is already over 4 years old when it reaches us. The light from the Andromeda Galaxy is a 2.5 million-year-old postcard from a time when early humans were first learning to shape stone tools. Astronomers take advantage of this universal delay to peer deeper and deeper into history. The more distant the object, the older the light we see. Some of the faint smudges in our telescopes are galaxies that formed when the universe was only a few 100 million years old. We do not see them as they are today, grand, mature galaxies billions of years in the making, but as fragile infant collections of stars still blazing into existence for the first time. This is where light becomes more than just illumination. It becomes a messenger. It tells us about the chemistry of distant stars, the speed of receding galaxies, and even the invisible gravitational fields they inhabit. Each photon is a traveller carrying information about where it came from and what it passed through. When we collect enough of these messengers, we can reconstruct the cosmic story with surprising clarity. Push this time travel to the extreme and you eventually reach the edge of what is visible, the cosmic microwave background. This is not the light of galaxies or stars, but the afterglow of the universe itself set free when the cosmos was still in its infancy. Roughly 380,000 years after the Big Bang, the universe cooled enough for electrons to bind with protons, forming the first atoms. Before that, the cosmos was a hot, opaque fog where light could not travel freely. When the fog cleared, light burst forth and has been moving outward ever since, filling the universe with a faint microwave glow. We have built instruments to detect this relic light, and what they reveal is astonishing. The cosmic microwave background is almost perfectly uniform, but not quite. Tiny variations in its temperature, differences of just a few millionths of a degree, show where matter was slightly denser in the early universe. Those tiny clumps, under the pull of gravity, grew into the galaxies and galaxy clusters we see today. In a very real sense, looking at the cosmic microwave background is like looking at the baby pictures of the entire universe. The wonder of looking back in time is that we can trace a continuous thread from those first atoms to the complex structures of the modern cosmos. We can see the gradual emergence of the first stars, their light pushing back the darkness in an era called Ryonisation. We can watch galaxies collide and merge, triggering new waves of star formation. We can even catch glimpses of ancient supernovae whose explosions seeded space with the heavier elements, carbon, oxygen, iron, that would eventually make planets, oceans, and people possible. And yet, there is a poignancy to this view. When we look at a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. We have no idea what it looks like now. It may have grown into a magnificent spiral, or it may have collided with a neighbour and transformed entirely. The light we see is an unchangeable record of a moment long past, and by the time we receive it, the moment itself is gone forever. This time-delayed reality is so normal in astronomy that we often forget how strange it really is. Imagine if everyday life worked like this, if speaking to someone meant hearing their reply years later, or if taking a photograph meant capturing not their current self, but their distant past. For astronomers, this is simply the nature of the job. The idea that the universe is a history book written in light also shapes the way we plan our observations. We know that to study the early universe, we must look for the faintest and most distant light possible, often redshifted into the infrared by the stretching of space. Telescopes like the James Webb are designed precisely for this task, able to capture the whispers of galaxies that existed before the Milky Way was even formed. In a way, the night sky is like an enormous, ever-changing archive, and our job is to collect as many volumes as we can before time and expansion hide them from view. Some of these records will be available for billions of years, but others, especially the most distant galaxies, are already slipping away, their light stretched into wavelengths too faint for our instruments to detect. The speed of light may feel like a limitation, but without it, this natural time machine would not exist. We would see everything as it is right now, stripped of history, stripped of story. The speed limit of the universe gives us the gift of perspective, the ability to watch the cosmos not only as it is, but as it was across its vast and intricate timeline. Each point of light in the sky is a messenger from the past arriving after an unimaginably long journey through space and time. Together they form a grand cosmic diary, one that begins with a hot glowing fog and stretches across billions of years to the universe we know today. And as we read it, page by page, photon by photon, we come to realize that looking into the night sky is perhaps the closest thing we have to traveling through time itself. It is a strange thing to imagine, a universe without light, not just a dark night or a power outage, but a true permanent absence of new light being born anywhere. No stars forming, no galaxies glowing, no supernovae flaring, not even the faint spark of a dying ember in the cosmic fireplace. It is a vision of the far, far future, so distant in time that all of human history would be nothing but the tiniest blip at the very beginning of the story. The scenario is called the heat death of the universe, and it is one possible ending according to our best understanding of physics. The idea is rooted in the second law of thermodynamics, the principle that, over time, energy becomes more and more evenly spread out. Right now, the universe is rich in concentrated energy sources, blazing stars, hot gas clouds, swirling accretion disks around black holes. These are the cosmic engines that generate light. But over unimaginable timescales, those energy differences will fade. The universe will move toward a state of maximum entropy, where everything is balanced out and nothing more can happen. Stars will be among the first to go. The smallest, dimmest red dwarfs will burn for trillions of years, far longer than the universe has existed so far. But even they will eventually exhaust their fuel. Once the last star flickers out, galaxies will no longer have a source of fresh starlight. The night sky, even as seen from the heart of a galaxy, will look emptier and emptier. That is not the end of all illumination immediately. There will still be occasional bursts of light from unusual events. White dwarfs, the cores left behind by smaller stars, will cool slowly over billions of years, radiating heat into space. Neutron stars will do the same. Even black holes, once thought to be perfectly black, will very, very gradually lose mass by emitting Hawking radiation, a faint glow at the edge of the possible. But this process is agonizingly slow, taking far longer than the current age of the universe for even a small black hole to evaporate completely. Over time, these final light sources will fade away one by one. The night sky will no longer sparkle. Instead, it will be a cold, featureless dark, broken only by the faint whisper of ancient photons left over from earlier times, stretched by the expansion of the universe into wavelengths so long they are essentially undetectable. This is the quiet end of cosmic history. In the heat death scenario, there is no grand explosion, No sudden collapse, just a slow, inevitable dimming. As energy evens out, the ability to do anything with it disappears. Stars cannot form, planets cannot warm, and life, at least life as we know it, has no place to thrive. It is important to remember that this future is staggeringly far away. We are talking about timescales in which even the longest-lived stars are just brief moments. Trillions of years into the future, galaxies themselves may drift apart completely, their stars dimming and dying in isolation. Quadrillions of years later, the remnants of stars, white dwarfs, neutron stars and black holes, will slowly fade. Then, after unthinkable stretches of time, the black holes themselves will evaporate, leaving only an extremely thin soup of particles and incredibly long wavelength radiation. At that stage, the universe would be unimaginably cold and dark. No new light would be created anywhere. The photons still drifting through space would be so stretched by cosmic expansion that their energy would be almost zero. The universe would be a place where nothing changes, a silent, unending equilibrium. It might sound bleak, but in a strange way there is something peaceful about it. The universe would have reached a final resting state, free from the turbulence of star formation, supernovae and cosmic collisions. It would be a cosmic winter that never ends. And yet it is worth noting that this is only one possible fate. Physics is still evolving, and new discoveries about dark energy or the structure of space-time could point toward different endings. Perhaps a big crunch, a big rip, or even a cyclic rebirth. But if the heat-death scenario holds true, then light's long and glorious reign will one day come to a close. Until then, we live in an age of extraordinary brightness. The stars are still shining, galaxies are still forming, and the universe is still full of places where new light is born every second. We are here at a time when the cosmos is vibrant, dynamic, and bursting with energy. Perhaps that is the real takeaway. In the vast sweep of cosmic history, our moment is special. We exist during the era when the universe is still lit from within. Billions and billions of years from now, the last light will fade into the cold darkness, and the story of the luminous universe will end. But for now, we can look up, marvel at the glow, and know that we are living in one of the rarest and most beautiful times the cosmos will ever see. Light has never just been a physical phenomenon. Long before humans could measure its speed or describe it in equations, it was a symbol, a shorthand for hope, truth, and divinity. Across cultures and centuries, light has been a central metaphor in religion, art, philosophy, and literature, carrying a weight far greater than its physical presence. In many ways, its cultural significance runs parallel to its physical importance in the cosmos. Just as nothing outruns it in the universe, few symbols in human thought carry more momentum. In the world's oldest stories, light often marks the beginning of everything. In the book of Genesis, the very first act after the creation of heaven and earth is the command, "Let there be light." That light is not simply the glow of a star, it is the unveiling of order from chaos, the dawn of comprehension itself. Many creation myths share this idea, that light emerges as the firstborn of existence, separating day from night, clarity from confusion, and life from lifelessness. In Hinduism, light is tied to knowledge and consciousness. The festival of Diwali celebrates the triumph of light over darkness, good over evil. In Zoroastrianism, the eternal flame is a literal representation of divine presence. Even in Buddhism, enlightenment is portrayed as illumination, the mind lit up with truth. In art, light has been one of the most versatile and evocative tools for expression. Painters have used it not just to reveal form, but to convey emotion. Think of the golden halos in medieval icons, radiating sanctity, or the way Renaissance masters like Caravaggio manipulated stark contrasts of light and shadow to create drama and spiritual depth. In the Impressionist era, light became almost a character in itself, flickering across water, dancing through leaves, changing by the hour. light was no longer just what allowed us to see the subject, it was the subject. Literature, too, has always found in light a perfect metaphor for revelation and transformation. Writers use light to signify clarity, truth, and understanding. A light bulb moment in modern slang traces its roots to centuries of associating light with sudden insight. In Shakespeare's plays, love is often described in luminous terms. Juliet is the sun, banishing the darkness of Romeo's night. Poets from Emily Dickinson to Pablo Neruda have drawn on light to embody joy, freedom, or the bittersweet brevity of life. The speed of light, the fastest thing we know, adds a subtle layer to its symbolic weight. Physically, it sets the ultimate speed limit in the universe, but metaphorically, it mirrors the swiftness with which truth can transform a mind. A single moment of illumination, whether literal or figurative, can change everything instantly. It is no surprise that cultures often speak of lightning-fast inspiration, or the blinding clarity of understanding. In philosophy, light has often been paired with the idea of knowledge itself. Plato's allegory of the cave imagines people mistaking shadows on a wall for reality, until one escapes into the blinding light of the sun, a metaphor for enlightenment through reason. René Descartes used the phrase, "the natural light of reason," to describe the mind's innate ability to discern truth. Even modern philosophy still draws on this imagery, speaking of shedding light on a subject or illuminating an argument. Interestingly, darkness in these traditions is rarely just the absence of light. It is often ignorance, evil, or fear. This duality gives light its power. It is not simply brightness, but an active force pushing back against something else. And because light moves so swiftly, it carries an almost supernatural quality in the human imagination, an unstoppable, pure messenger. Science, of course, eventually grounded light in measurable properties, wavelengths, photons, and a speed that can be written out as exactly 299,792,458 meters per second. Yet even in the most technical descriptions, there is a poetry to the idea that this is the ultimate limit, that light speed is woven into the fabric of reality itself. Philosophers and poets might not care about the fine details of electromagnetic theory, but the fact that light represents the fastest possible connection between 2 points only strengthens its symbolic role as the carrier of truth, hope, and divine will. Cultural symbolism also reflects light's role in survival. Long before street lamps or electric bulbs, light meant safety, the glow of a campfire keeping predators at bay, the sunrise bringing warmth after a dangerous night. This primal association with protection and renewal still echoes in the way we speak. A guiding light, a beacon of hope, a light at the end of the tunnel. Even in our technologically saturated age, a candle in the dark still stirs something deep in the human psyche. The speed of light also plays into the modern mythos of instant connection. In an age where information travels across the globe in fractions of a second, we are, in a very real sense, living in light's domain. Fibre optic cables pulse with laser light to carry our voices and thoughts across oceans. Satellites bounce sunlight and radio waves back to Earth to connect people on opposite sides of the planet. This modern reality makes light not just a metaphor for communication, but the literal medium of it. In cinema, light has continued to be both tool and symbol. Directors like Stanley Kubrick, Terrence Malick, and Wong Kar-wai have used natural light to create mood and meaning, while science fiction films lean into the drama of beams, pulses, and flares as signs of technology and transcendence. Even here, the link between light's physical qualities and its deeper meanings remains strong. It is fast, powerful, and capable of revealing or destroying in equal measure. Ultimately, light occupies a rare space in human thought. It is both everyday and eternal, practical and sacred. We can flick on a switch and flood a room with it, but we can also contemplate it as the purest metaphor for knowledge, goodness, and the divine. And while science has stripped away some of the mystery, it has only added to the awe. To know that light is not just fast, but the fastest thing there is, makes its symbolic role even more fitting. It is possible that billions of years from now, light will no longer be created anywhere in the universe. If the heat death scenario plays out, the cosmos will one day be dark. But even then, the legacy of light in culture, philosophy and art will remain as long as there are beings who can remember it. For now, every sunrise, every flicker of a candle, every ray breaking through clouds is part of a story as old as humanity. The story of seeking, finding and cherishing the light. For something that holds the title of fastest in the universe, light is surprisingly calm about it. It never rushes, never slows, never varies its pace for anyone or anything. Whether it is streaming from the heart of a star, bouncing off a mirror in a laboratory, or crossing the void between galaxies, it always moves at the same steady rate. This constancy makes it almost meditative, a reminder that speed does not always mean haste. From a physics standpoint, the stillness in light speed comes from its nature. The value of 299,792,458 meters per second is not just a record-breaking performance. It is a property woven into the structure of space-time itself. In a vacuum, nothing changes it. Light does not tire, it does not accelerate, and it does not need a push. It simply is. In a way, it is the ultimate example of an object being perfectly itself. This constancy allows it to act as a kind of universal clock. Because it moves at the same speed everywhere, scientists can use it to measure vast distances and enormous spans of time with astonishing precision. The light from a distant galaxy becomes both a messenger and a stopwatch, carrying information and the record of how long it took to arrive. Even though we think of it as fast, light's reliability means it can be patient, taking billions of years to cross the cosmos without losing a fraction of its speed. There is a strange serenity in that idea. Light born in the first seconds after the Big Bang has been travelling for almost the entire age of the universe, passing through unimaginable spaces without complaint. It does not seek shortcuts or sprint ahead in bursts. It flows with an unchanging grace, like a river that always moves at the same current, no matter the weather. This paradox of something moving unimaginably fast yet embodying stillness says something about our own human notions of speed and urgency. We tend to link speed with restlessness, as if going faster means being more frantic. Light shows us a different model: velocity without stress, momentum without chaos. It does not race other forces or measure itself against a finish line. It moves because that is what it does, not because it is in a hurry to arrive. Its constancy is also the reason it defines so much of our understanding of the universe. The equations of relativity, the concept of causality, the way time and space interact, all rest on the speed of light being unshakable. If it wavered even slightly, our measurements would crumble, GPS satellites would fail, and the delicate balance of cause and effect could be thrown into disarray. The stillness behind light's speed is not just poetic. It is the reason the universe is coherent at all, even in the face of vast cosmic events, supernova tearing apart stars, black holes warping space-time, galaxies colliding. Light remains unfazed. It emerges, or is bent, or is absorbed. But wherever it travels freely, it keeps the same pace. It does not pick up speed when leaving a star or lose momentum drifting through the cold void. The universe may be turbulent, but light carries on with the same measured stride. This quality makes it a quiet equalizer in the cosmos. No matter where you are, if you send a photon into the void, it will travel at the same speed as any other photon anywhere else. A beam from a torch on Earth and a flash from a quasar 10 billion light-years away share this unbreakable rule. The light from both might take wildly different amounts of time to reach a destination, but the speed itself never changes. From a philosophical angle, there is something humbling in recognizing that the universe's ultimate speed champion has no ego about it. It does not flaunt its record. It does not need to because nothing else can match it, not by choice, but by the very structure of reality. Light's patience comes from the fact that it never has to prove itself. In human history, this unhurried speed has been a gift. It allows us to look deep into the past, to see ancient light that has crossed the gulfs between galaxies. That light could not have made the journey if it had burned itself out in a sprint or slowed along the way. It made the trip by simply maintaining what it always does, steady, unwavering motion. When you think about it, the stillness behind light's speed is a kind of cosmic reminder about endurance. It shows that constancy can achieve as much as, and often more than, bursts of frantic effort. Light reaches across unimaginable distances not by rushing, but by moving with perfect consistency over incomprehensible spans of time. And perhaps that is why, despite its blinding swiftness, light feels so calm. It does not live in our human scale of minutes and deadlines. It operates on the scale of universes and eons. 1 billion years is nothing to it. It will keep going long after our sun fades, carrying messages across an ever-expanding cosmos, still at the same pace, still without hurry. In the end, Light's story is not just one of speed. It is a story of reliability, of a constant thread weaving through the fabric of space and time. Its swiftness may make it famous, but its steadiness is what makes it profound. In the quiet persistence of its motion, light embodies a kind of patience that even the universe's vastness cannot exhaust. That is the paradox. The fastest thing in existence is also the most patient traveller we know. From the moment we first tried to grasp what speed truly means to our slow, careful journey through centuries of discovery, we have been following light, not just as a physical phenomenon, but as a guide. We started with the simple curiosity of wondering how fast something could move, and ended up confronting one of the deepest constants in nature. Along the way, we traced light's path through history, watched how clever minds found ways to measure what once seemed unmeasurable, and learned why this number, 299,792,458 meters per second, is more than just a statistic. It is a cornerstone of the cosmos. We have seen how light speed is not an arbitrary limit set by some universal authority, but an intrinsic part of how reality works. It is baked into the fabric of space-time itself. We have explored how nothing with mass can reach it, and why massless particles like photons and gravitational waves must move at it. We have navigated the strange world of relativity, where time bends, distances shrink, and the universe plays by rules that can feel more like poetry than physics. We have learned that while light can be slowed in glass or water, nothing truly outruns it in the vacuum of space. Even the illusions of faster-than-light motion, in quantum entanglement, in cosmic expansion, in astronomical tricks of perspective, are just that, illusions. The speed limit stands firm, not out of stubbornness, but because it is tied to the very definition of cause and effect. Without it, the sequence of events in the universe would unravel. We have travelled in thought to the edge of the observable universe, to the cosmic horizon where light's long journey since the Big Bang defines the limit of what we can ever see. We have used it as a time machine, looking back at ancient galaxies and the faint whisper of the cosmic microwave background, the afterglow of creation. We have even looked forward, imagining a far future when the universe is cold and dark, when new light no longer shines, and the constant speed we know so well continues on in silence. And we have reflected on the paradox that the fastest thing in existence is also the most constant patient traveller we know. Light does not sprint, it does not surge, it simply moves, unchanging for as long as space exists for it to cross. It connects us to the deep past, binds us to the far reaches of space, and gives us a universal standard against which to measure both distance and time. If you think back to the questions we began with, about the meaning of speed, about whether the universe could have chosen a different limit, about what would happen if this constant were not so constant, you may find that the answers we have uncovered are both satisfying and humbling. Satisfying, because physics gives us a coherent picture of why light's speed is what it is. Humbling, because this picture reminds us that our human intuitions are often shaped by a tiny corner of reality, while the cosmos operates on scales and in ways that far exceed our everyday sense of motion and time. Light speed shapes everything we know and everything we can know. It defines how far we can explore without waiting beyond a human lifetime. It means that when we gaze at the stars, we're always looking into history, seeing them not as they are now, but as they were when their light began the journey to us. It sets the stage for the drama of the universe. Galaxies forming and colliding, black holes swallowing light itself, cosmic structures unfolding across billions of years. And through it all, light remains the messenger, bringing us news from across the depths of space. There is comfort in this constancy. Whether you're lying awake, tracing the arc of the Milky Way in your mind, or letting your thoughts drift towards sleep, light is still on its way. It is crossing oceans of emptiness, slipping past planets and dust clouds, carrying with it the story of where it came from. Long after we are gone, it will still be travelling, still at the same pace, still unhurried. And perhaps that is the most enduring lesson hidden within the physics, that speed is not only about urgency, but also about persistence. Light does not need to race to be fast. It simply continues, and by doing so, it spans the universe. It reminds us that sometimes the most remarkable journeys are not the ones that happen in a flash, but the ones that endure, steady and sure, for as long as time itself. Whether you are listening with a curious mind wide awake or with eyelids growing heavier, the truth remains the same. Somewhere, right now, photons are leaving the surface of a distant star, beginning a voyage that may take millions or billions of years before they ever find an eye or an instrument to receive them. They do not know who will be there at the end of their journey. They only know how to travel, and that they will do so without pause. Light is always on the move, and yet in its constancy it is always at rest with itself. That is its secret. That is its gift. And as you consider its endless patient motion, whether in thought or in dreams, remember that you are part of its path too. Somewhere light is already on its way to you.